Matematika. Today we're going to do 2.3 exponential functions. We'll start with the graphs of exponential function. To draw the graph of an exponential function, we can use a variety of strategies, including completing a table of values for the function and drawing the curve through the points found, and using technology such as a physical or a line graphing calculator, and identifying the key features from the equation. So an exponential function could also have a leading coefficient, which would be written in the form of f of x equals a b to the power of x, where a is the y-intercept and b is the constant factor. So the y-intercept is the value of a. Now check this by substituting x equals 0 in the function of y equals a times b to the 0. Remember, any number or anything that is raised to the 0 power, that's equals to 1. So that means that's 1. A times 1 is still equals to 1. And the y-intercept is 0, comma a. Okay, 0a. The exponential function, the base, okay, must be positive value other than 1. So these are the conditions. When will we know that the function is decreasing, and when will we know that the function is increasing? When the b is between 0 and 1, the function is decreasing, or b less than 1, the function is decreasing. When b is greater than 1, the function is increasing. Okay, let's remember that. The leading coefficient a can be any real number, and it determines the range of the function. The a is the one that will determine the range of the function. So when a is greater than 0, the range is y greater than 0. When a is less than 0, the range is y less than 0. We'll be using all these features later on when we do some problems. Okay. Now, if you are given here, there's a graph wherein the two curves intersect at a certain point. Okay. This one, the green one, is a graph when b is greater than 1. That means it curves that way. Okay? From here to the line until it gets 0 here. When it faces up, facing to the left, that is b greater than 1. When the blue one here is facing to the right, it curves. That means the b is less than 1. So what happened when the b is less than 1? This is decreasing. All right? This is when b is greater than 1. This is increasing. That's how the graph looks like. So the key features of exponential function can be both found in the equation and the graph. So if you are given f of x equals a b to the power of x, a represents the y-intercept, and it is plotted at the point 0, A. When B is between 0 and 1, or B is less than 1, the function is decreasing. So when B is greater than 1, the function is increasing. Okay? So the value of A here is the y-intercept, but it also affects the range of the function and tells us more about the range of the function. So let's move on. Let's look at how the graph goes. Regarding the range greater than 0 and the range is less than 0. All right, we have it here. So this is greater. Y is greater than 0. That means this is increasing, and that is how it looks like. So A greater than 0, B is greater than 1. When Y is greater than 0, okay, decreases at a decreasing rate. That is A greater than 0, but B is less than 1. This is how the graph looks like. And this is decreasing. Okay, you have that as decreasing. But when the Y is less than 0, this is where the direction of the curve, when it's less than 0, it seems like it's turned upside down. It decreases at an increasing rate. Okay? Decreases at an increasing rate. And here, when Y is less than 0, increases at a decreasing rate. A less than 0. A less than 0. B greater than 1 here. And B is less than 1. All right. What else do we need to know? The exponential parent function, y equals b to the power of x, can be transformed as to y equals a times b to the power of c times x minus h plus k. There is a transformation going on here. If a is less than 0, then the graph is reflected across the x-axis. Like in this case here. If the graph faces up here, the graph is reflected at the x-axis and becoming that one when a is less than 0. The graph is stretched or compressed vertically by a factor of a. If c is less than 0, then the graph is reflected across the y-axis. The graph is stretched or compressed horizontally by a factor of c. Then the graph is translated horizontally by h units, and the graph is translated vertically by k units. All right, so let's start with the problem. Consider the table of values for the function f of x. X is negative 1, 0, 1, 2, 3, 4, while f of x is 5 third, 5, 15, 45, 135, 405. Determine whether the function represents an exponential function or not. Now, what are we going to do? Now, remember that to determine if the set of data represents an exponential function, we want to compare the successive y values, like 5 thirds, then it becomes 5, 15, 45, 135, 405. And determine if there is a common ratio. So if f of -1 is 3/5, I have it here. F of -1 is 5/3. And then f of 0 is 5. So if we want to calculate the common ratio, we're going to take that as from 5/3 to 5. So that means we can have this as 5/3 times b would be equals to 5. Right? Where b would be 5 times 3/5. Do the reciprocal. When you transpose, so b is equals to 3. You cancel that out. What happened here, when you do that, when you transpose or when you divide 5/3 and then you divide by 3, remember the denominator of 3 is 1. So you multiply the reciprocal of 3, which is 3/5. Or we do that 1/3. Right? Okay. Now the common ratio, we have now the common ratio, which is equals to 3. And then we want to check if the factor works in the remaining, like 15, 45, 3, 405. So for example, we'll check 5 times 3. We have 15 for the next one here. 15 times 3 for the next one. 15 times 3, we have 45. Then 45 times 3, we have 135. Then the last, we have 135 times 3 is giving us 405. That means the function, therefore this function represents an exponential function. Okay, so this is an exponential function. Let's have letter B. Write an equation to represent the exponential function. So the function has a y-intercept. Let's look at the, okay. We're gonna look where we can find the y-intercept. The function has a y-intercept. When x equals 0. Okay, let's look at this table right here. When x equals 0, the y is equals to 5. And the growth factor, this is growth because it's increasing. And the growth factor is how much? It's 3. That is our ratio. That's the growth factor. So if you are asked to write an equation, you could say that the function of x would be equals to, starting for 5, where the y-intercept is. The y-intercept is at 0, 5. So starting at 5 times, it should be, okay, I'm going to write the formula ab to the power of x. So our b is 5. I mean, a is 5 and the b is 3 to the power of x. This is the equation. All right? Let's have number 2. Identify the function as identify the function is exponential growth or decay, and justify your answer. So looking at the f of x, remember the function is a b to the power of x. All right. When can we determine? We have it here. When can we determine whether it's growth or decay? When b, this is where our b is, would be between 0 and 1. 2/3, that's point something, that's less than 1. And a is greater than 0. So this is a decay. Why? Because of the b. B is between 0 and 1. So what is our reason for this? Because a is greater than 0 and b is greater than 0 but less than 1, or between 0 and 1. And this is 2 divided by 3, that's point something. In this case here, a is greater than 0, right? But the b, it's still between 0 and 1. It's still less than 1, right? So that means this is decay. Letter C, 5.7, okay, a is greater than 0, but our b is still between 0 and 1. So this is still a decay. All right. A here is greater than 0, but the b is also greater than 1, right? So when this happens, a greater than 0 and b is less than 1, I mean greater than 1, then this is a growth, exponential growth. We're just trying to identify whether it's decay or growth. Okay, let's have this problem. The following values are output values of an exponential function of the form f of x equals a b to the power of x, where a and b are constants. Write the function along the input value that represent the output value. Remember that if you have 7 times 7 times 7 times 3 times 4, what do you think is being repeated here? 7 is being repeated. So your A, which is the initial value, would be the 3.4. Okay. And what would be our function? 7 to the power of 3, because it has 3 times. Or without writing that, let's have the function to the power of x, where x is equals to 3. Right? Let's have this. 6 times, letter B, 0.8, 0.8, and 5.2. So our function would be 5.2 times 0.8 to the power of x. And what does x means? How many times the 0.08 being multiplied? 2 times. Okay. Let's have this. 6 times 1.3, 1.3, 1.3, 1.3. So our function would be 6 as the initial. Then the b is 1.3 to the power of x, where our x will be 1, 2, 3, 4. Right? The last we have 9 times 9 times 9. We don't have first initial, that means f of x would be 9 to the power of x, and the x would be equals to 3. All right. Let's have this problem. For each scenario, find the equation of the transform function. So we have 2 graphs here. One is the transform 1. So the f of x will be this dotted green curve, while the transform curve will be the solid line. Okay. The graph of f of x is translated to get the graph of g of x as shown. Okay, let's do our observation. We notice that the y-intercept, okay, so where is our y-intercept? When I will increase the graph here. Our y-intercept should be when x is 0, there is a value of y. So maybe right here. Okay? That is the y-intercept. What else would that be? The y-intercept, sorry for that. I need some water. Okay. F of x has been translated 2 units to the left. Okay, let's say somewhere here. 1, 2. This is the location of G. The new one, untranslated, 3 units up. This is 2 units and 3 units up. That's the translation. Like here, if this is the y-intercept, it translated 2 units and 3 units up here, where the location of 3, 2. 3 units up, 2 units to the left. Okay, that is the translation that is being done in this graph. And then, what else do we need? So, the units obtained, in this case here, we have a -2 right here, and then 4, 1, 4 right here. So this is -2 location of the new point. That is from here, and the new location of that point. That is where the translation is taking place. Since the graph has only been translated, the base of both exponent function will be the same. We can determine the base by finding the ratio of the consecutive outputs of the parent function and finding the ratio of differences of consecutive outputs and transform it. Okay, let's look at the how we are going to do that. So I'm gonna write here. So that transform form transform function will be in the form of y equals bx plus h plus k, where h is 2, that is to the left 2 units, and k is 3, that's 3 units up. So looking at the transform function, we can easily identify the points -2, 4, and where is -1, 6. These points right here, -1, 6. And what other points do we have? This is 0, the y-intercept, 0, 12. We could easily identify these points. So analyzing the change in the values, we find that, let's say, the first one, when x equals, let's say when x is -2, it becomes, the y becomes 4. Okay? When x is -1, the y becomes 6. That increases by 2. When x is 0, it becomes 12. The y becomes 12. So what's the increase here? It increases by 6. So the ratio of difference in these outputs is, okay, if we try to get the ratio here, it will be 6 divided by 2, which is equals to 3. Okay, this means that B is equals to 3. So we could make the g of x should be 3 x plus 2, then plus 3. That's the vertical shifts. Okay. All right, let's have the letter B. The graph of y is equals to 1/2 to the power of x is reflected across the x-axis and stretched vertically by a factor of 2. So we can represent it by looking at this graph. Stretch vertically. So the reflection across the x is equivalent to by multiplying output values by -1. Okay? So if we have originally this one right here, then we multiply it by a -1. A vertical stretch by a factor of 2 is equivalent to multiplying the output by 2. Alright? So apply the idea of the transform. That would be y equals -2 times the 1/2 to the power of x, because that is where the initial value is. All right. So if we look at the, if we try to check, let's do this by having a table and check. Okay, I'm going to transfer here. Y equals -2, then 1/2 power of x. I try to make a table out from the graph. Let's say this is x. So let's have the value of x when -3. It is 8 right here. So -3. The f of x is 8. When it's -2, it's 4. Then when it's -1, right here, it is 2. Right? So when it's 0, it's 0 right here. So what between 0 and 2, that is 1. When it's 1, right here, 1/2 of 1, I could say that it's 1/2 of 1. So I say 1/2. So the last will have, when it's 2, almost closer to 0. That is 1/2 of 1/2. That's 1/4. Estimate. Because the graph is somewhat like very close now to 0. Well, the new graph, it says that 2 times equivalent by multiplying the output value by 2. So 8 8 multiplied by -2 right here, that's -16. So 4 multiplied by -2, that's -8. 2 times -2, -4. 1 times -2, it's -2. 1/2 times -2, that's -1. and then 1/4 times negative 2, that is negative 2 over 4, which can reduce as negative 1/2. So, by looking at the g of x, all right, so this is and so on and so forth. So might as well when it's 3. Then let's do the 2. It is negative 2 right here, right? When it's 1, it's negative 4. When it's when it's 2, okay, 1 negative 4. When it's 0, it is negative 2, right? When it's negative 1/2, it is negative 1. And when it's 1/4, it is negative 1/2 right here. So this one is the g of x, and this one is the f of x graph. All right. I hope that is somewhat like clear. Okay, let's do this one. The graph of the function f of x is 5 times 2 to the power of x. So it's very clear that the initial value, or the y, okay, is 5, is translated to 10 units down and give us a g of x. So this is the f of x, and this is the g of x. Excuse me. Sorry for that. All right. Complete the table of values f of x is transformed. When g of x, then sketch the graph. Okay. So if x is negative 2 without the graph, okay, so 5 times 2, when x is negative 2, how much would that be? That would be, when you have a negative exponent, get the reciprocal to make it positive, 2 to the 4th. So 5 times 1/4, that is equals to 5 over 4, right? So this is 5 over 4. So we have a lot. So I can do it here. 5 times 2 to the power of negative 1. That's 5 to 1 over 2. So you have 5 over 2. When x is 0, remember anything that is raised to 0, that's equals to 1. So that is 5 times 1, that equals to 5. Okay, 5, 2 to the first power. So that is 5 times 2, that is 10. 5 times 2 to the second power. So 5 times 4, that is 20. All right. 5 times 2 to the third power. So 5 times 8, that is 40. Then you have 5 times 2 to the power of 4. That is 16 times 2 times 2, 4 times 2, 8, 5 times 16. That is 80. Right? So we need to get the g of x. Alright? As the graph is translated 10 units down, the g of x would be f of x minus 10, since it's translated 10 units. So we can subtract 10 from each value in the table for f of x to find the corresponding value of g of x. Okay, subtract 10. So we have for g of x, so let's use this 5 over 4 minus 10. So how would we transform 10 into a fraction? That would be 5 minus 4 over 10, times 4. That would be 40 over 4. So that's negative 35 over 4. So this is negative 35. Negative 35 over 4. Let's do 5 over 2 minus 10. So that would be 20. Turn it into a fraction. 5 over 2 minus 20 over 2. That is negative 15 over 2. Alright, let's have 5 minus 10. That's negative 5. 10 minus 10, that's 0. Then 20 minus 10, that's 10. 40 minus 10, that's 30. Then 80 minus 10, that is 70. So we have the graph. We completed the table, and we have the graph is being translated in this problem and form from the parent graph, which is what would be the parent graph here. Let's say p of x would be 2 to the power of x. So the parent is stretched vertically by a factor of 5 to obtain the graph of f of x. So then we translated f of x down 10 units. So let's see. Where is the negative 2 here? Right here. So maybe this is negative 35 over 2. That is negative 35 over 4. Wait, I'm gonna get my calculator to have a fixed value in the graph. Wait a minute. Um, 35 divided by 4. What's going on? Oops, something's going on. 35 divided by 4. Sorry guys, something's wrong with my calculator. Divided by 4, that's 7. Divided by, oh, what's wrong with me? 7 times 4, that's 20. Oh, 7 point something. So this is 7 point something here. Okay, negative 15 by 2, that is 7.5. Somewhere here in the middle. They're very close. They are very close. When it's 0, it's 5. So between, right here, between 0 and 10. And when it's 1, it's 0. All right. So this is how it should be. When it's 2, it's 10 right here. When it's 1, it's 0 right here. When it's 0, it's negative 5 right here. Right here, I mean. All right. I have plenty of points. When it's 3, it's 40. All right. I mean, it's 30. When it's 4, it is 70. Right there. If you look at your new graph, and then when you're going to plot, actually we can do this by using our, if we are using a calculator. Okay, so we're done. Let me say this. If I can do it, so can you. Don't forget to hit the like button and subscribe. See you in my next video.